Have you ever gazed at the moon and pondered the secrets it holds? Our silent celestial neighbor isn't just a dusty rock. It carries a faint, ancient magnetic memory. Scientists are now working, like cosmic detectives, to unravel this lost magnetism. Why? Because understanding the moon's ancient magnetic field offers a thrilling glimpse into the chaotic childhood of our solar system. Here's the puzzle. The moon today doesn't have a global magnetic field like Earth. Yet lunar rocks from the Apollo missions and data from orbiting spacecraft show that parts of the moon, especially on its far side, are surprisingly magnetic. So how did these rocks get magnetized? Early theories suggested the moon once had a molten core that generated a weak magnetic field, a dynamo, much like Earth's. But this early dynamo alone probably wasn't strong enough to magnetize surface rocks to the extent we observe. This is where the story takes a dramatic turn, with asteroids playing a starring role. Picture this: a colossal asteroid slams into the moon. Think of the impact that carved out the enormous Imbrium basin. Such an event would have instantly vaporized lunar rock, creating a superheated cloud of electrically charged particles, a plasma. Computer simulations reveal this plasma cloud would have enveloped the moon, with a massive portion surging to the side directly opposite the impact point. As this plasma converged, it could have temporarily, but dramatically, amplified the moon's existing weak magnetic field in that region. Any rocks cooling down in the presence of this supercharged field would have recorded its powerful signature. This fascinating process could explain the strong magnetic anomalies we detect on the lunar far side, which often sits opposite several major impact basins. Researchers also found that material ejected during these impacts, including iron-rich bits from the asteroid itself, would travel and accumulate on the opposite side of the moon. Heated by the shockwave, this debris would cool and lock in a record of the moon's magnetic field at that precise moment, roughly 4 billion years ago, when many large basins were formed. So what's the timeline for the moon's own magnetic dynamo? Paleomagnetic studies tell us the moon had a dynamo, generating a field starting at least 4.25 billion years ago. This early field might have even been as strong as Earth's current magnetic field, but it weakened significantly by about 3.2 billion years ago. Evidence from lunar rocks suggests the dynamo likely switched off for good sometime between 1.92 and 0.80 billion years ago. Scientists think the prolonged existence of this later, weaker field might have been powered by the slow crystallization of the lunar core. Studying the moon's magnetic past is more than just lunar geology. It helps us understand the intense bombardment period of the Earth-Moon system and the turbulent conditions of the early solar system. Future missions, including those under NASA's Artemis program exploring the lunar South Pole, could give us the chance to directly sample these magnetized rocks. Analyzing them for shock from impacts alongside their magnetic properties could finally prove the impact-amplified magnetic field theory, giving us a clearer window into the moon's ancient magnetic heart. What a story our moon has to tell! Stay curious.